Hi, Dr. P here, and in this lecture we'll take a look at the concepts of enthalpy, the concept of enthalpy, and the technique of calorimetry. So enthalpy is a state function and we're going to use the abbreviation H for it. And the definition is H equals U plus PV. Enthalpy equals the internal energy plus the pressure times volume. Now, what is enthalpy really? Well, let's consider a process carried out at constant pressure, where the only work allowed is pressure volume work. So if you remember from last time, we had the expanding piston and a cylinder. So we're doing that. We have a constant pressure and we're doing an expansion. So that's the only type of work we're going to do. So in this case, we have, so let's just say here, process at constant pressure, only PV work allowed. So that means our work equals minus P delta V from last time. So our delta U equals Q, and we'll call it QP for constant pressure, plus W. That then becomes delta U equals QP minus P delta V. Delta U equals QP minus P delta V. Delta U. I think I misspoke and called it delta W. Delta U. Or we can rearrange this so we can rearrange it in terms of QP equals delta U plus P delta V. Now, let's look at the change in enthalpy. So we'll look at delta H. So delta H equals delta U plus delta PV. But pressure is constant, so really we have delta H equals delta U plus P delta V. Because remember, P is constant. So I can go ahead and say, wait a minute, these guys look awfully similar. So delta H equals QP. So if I was going to describe delta H in words, I would say at constant pressure, where only PV work is allowed, the change in enthalpy, delta H, of a system is equal to the energy flow as heat. So you can think of enthalpy as heat, more or less. It's energy in the form of heat. And we'll talk about something called heat of reaction, sometimes called enthalpy of reaction, which is the change in enthalpy of a reaction. So delta H is going to equal our enthalpy of our products minus our enthalpy of our reactants. Now we won't necessarily be able to directly measure our initial enthalpies, initial and final enthalpies, but we will be able to measure delta H. If delta H is greater than 0, the reaction is endothermic. Heat is flowing into the system. If delta H is less than 0, the reaction is exothermic. Heat is flowing out of the system. So this is important stuff here that you guys should know. Now we're going to measure delta H using calorimetry. So let's go ahead and take a look at what calorimetry is. So calorimetry is the science of measuring heat. So we'll use something called a calorimeter to measure heat. And what we're going to do is observe a temperature change, delta T, when something absorbs or gives off energy as heat. So we'll say observe delta T when heat absorbed or given off. And different substances may require different amounts of heat to change the temperature a given amount. And that's called the heat capacity. So we'll call that big C. And that's going to be our heat absorbed divided by our increase in temperature, T. But the amount of substance is important. So we're going to use specific heat capacity, sometimes just called specific heat. And so now our specific heat, we'll use a lowercase c, is going to be heat absorbed divided by increase in temperature per gram. So it'll be heat absorbed divided by, I'm just going to call it delta T, and then this is per, this whole thing is per gram, so delta T times, we'll just say mass here. And our units will be joules per gram degree Celsius, or joules per gram times Kelvin. We can also have something called a molar heat capacity, where our units are joules per gram, joules per mole degree Celsius, or joules per mole Kelvin. So specific heat is the heat capacity per gram of stuff. Molar heat is the heat capacity per mole of stuff. Interestingly, most substances have very similar molar, or approximately similar molar heat capacities, but they will have very different specific heats. For example, water has a relatively high specific heat of 4.184 joules per gram degree Celsius. So we can make a simple calorimeter And I talked about this a little bit in lab. You guys get to do stuff with simple calorimeters in lab. So we'll go ahead and we'll have some kind of insulating cup. Styrofoam cup and lid. And then in here we'll have some solution, and then we'll have some kind of little stir here, little paddle stir here. Solution, here's our stir. And then we'll have also our thermometer. And this is something called, or this technique is called constant pressure calorimetry. You can read about other types of calorimetry in the textbook chapter. There's something called a bomb calorimeter, which is used to measure the total energy of something that is combustible. But this simple styrofoam cup calorimeter is useful for measuring heat released for a variety of processes. It could be measuring the heat capacity or measuring the specific heat of a metal. It could be measuring the heat of a reaction or the heat of mixing. So let's say we have the following. Let's go ahead and take as an example here. So we'll mix 50.0 ml of 1.0 molar HCl at 25 degrees Celsius with, let's do 50 milliliters ml of 1.0 molar NaOH at 25 degrees Celsius. And then after mixing, the temperature equals 31.9 degrees Celsius. Thus, our net ionic equation, H plus OH minus, reacts to give H2O, must release heat. Otherwise, how else would the solution warm up? Now we know that 4.18 joules are required to raise the temperature of 1 gram of water 1 degree Celsius, because that's the specific heat of water. So our energy released by the reaction is going to equal our energy absorbed by the solution. That is, the water, the solution is mostly water. So our energy released is going to equal our mass of solution, or water, times our specific heat for that solution times delta T. Or we would say MC delta T. So for the example, excuse me, our energy released equals, our mass is 100, 100.0 times 10 to the 2 grams. We have 50 milliliters and 50 milliliters. That adds up to 100.0 milliliters. That's not times 10 to the 2. I'm sorry, that's just 100 grams. Sorry, I have it written differently in my notes here. 100.0 grams times 4.18 joules per gram degree Celsius times, what's delta T? Delta T equals T final minus T initial, which is going to equal 31.9 minus 25 equals 25.0 equals 6.9 degrees Celsius. So 6.9 degrees Celsius. So my degrees Celsius cancel, my grams cancel, and then I end up getting 100 times 4.18 equals that times 6.9 equals 2884.2. So I get 2.9 times 10 to the third joules. That would be the amount of energy released by this particular reaction. Now, if I used twice as much reactants, I would get twice as much energy. Thus, we say the heat of reaction is an extensive property. It depends on how much stuff we have, as opposed to intensive properties like temperature, which are not related to the amount of substance. It doesn't matter how big something is at 25 degrees Celsius, it's still at 25 degrees Celsius. We often express enthalpies of reaction in terms of molar quantities. So in our example, let's say in this example, we have our moles of H plus equals 50.0 milliliters times 1.0 moles H plus per liter times 1 liter per 1,000 milliliters. 1 liter. Milliliters cancel, liters cancel, and we end up here getting 50 divided by 1,000 equals 0.05, 0.050 moles H plus. So our delta H then is equal to minus 2.9 times 10 to the third joules, because it is given off by the reaction. Okay, it's negative because the heat is given off by the reaction. Heat is leaving the system. We'll divide that by 5.0 times 10 to the minus 2 moles H plus. 5.0 times 10 to the minus 2. I just happen to write that in scientific notation. And that ends up equaling minus 5.8 times 10 to the 4th joules per mole, or minus 58 kilojoules per mole. Okay. Now we can also look at constant volume calorimetry where no work is done, and this is that bomb calorimeter that I talked about. And in this case, the reactants are placed inside a well-insulated container called a bomb and ignited. And the bomb container is sturdy, so it stays intact, and there's no change in the volume. And the energy change is determined by measuring the temperature of water surrounding the calorimeter and the other calorimeter parts. And so our internal energy change is equal to, we would call it QV, where it's heat at constant volume. Again, this is typically used to measure combustion or explosion reactions, and we won't be doing this, obviously. We'll be focusing on the specific heat at constant pressure. All right, so that's calorimetry in a nutshell. We'll talk more about it in lab, but I did want to, give you guys the background here. All right, so until next time, stay safe out there. Bye now.